Hello, everyone. Welcome. Before we start, do we have any gamers in the audience or anyone interested in gaming? There we go. Thank you. You're in the right talk. So here today, we're going to talk about how do you run game servers on top of Kubernetes. My name is Kamil Babuli. I'm a specialist solutions architect with AWS, and I'm here today with my colleague Ria.
Yeah, I'm Ria, and I am a solutions architect that exclusively works with games customers. So before we start, this isn't an awful survey, I promise. This is a game. So we're going to play a game at the end of this session, and it's a multiplayer online game. If you have not an iPhone, if you have Android,
there is no iPhone client, but
yeah, if you have Android or any other
laptops, everything else works.
You can follow the Bitly link. We're going to play this at the end, and I'm so bored of being flameur at this point, so I need some more challenges.
I'm going to keep the slide for a tiny second longer, but that link takes you to the game. So if you do Bitly get SDK.
We'll show the thing at the end as well. Yeah. Okay. So I just wanted to set the scene. What's a game server? I know quite a lot of you guys play games, but game server is just a server used to host and play multiplayer games. And that seems really straightforward, but the most important part about this is that it acts as the central point of authority for the games and the players. So how game server architecture works on a basic level, I'm going to move over here so I'm not in your way, is that you have the game server and the game client. The game client connects to the game server, and there's a constant loop of information. The game client is sending game actions to the game server, and the game server is constantly updating the game client with the game state. So how this works in actual reality is if me and Flameur are playing competitive apple picking game, I go to pick the apple using the game client on my local machine. So it could be a PC, it could be a console. Sure, people are going to be playing Call of Duty on their smart fridges soon. I go to pick the apple. My client says to the game server, Ria is picking this apple. The game server then checks if the apple exists, if I'm close enough to the apple to pick it up. It makes that decision, and it said, yes, you did pick up that apple. And it tells my game client that, and it tells Flameur's game client that through the game state. This is why you need a central point of authority, because if it was client authoritative instead of server authoritative, I, on my side, could potentially say, I've picked the apple. In fact, I've picked all of the apples, and I win the game. And then my game client would update the game state to the game server and to Flameur, and that would be cheating. Aside from cheating, another issue is that if I'm updating the game state from my game client, that happens first. The rest would then be relayed to Flameur and to the rest of the players, which would mean that I would be slightly ahead. It would be milliseconds, but it would still be enough to be a problem. So with traditional game servers, you would have multiple running on one large instance or one large box, which has its own issues. So if you're scaling it, you're scaling for multiple servers. It's harder to scale by increments because you may pop up an increment, have lots of compute left. Same as it's hard to right size because you're right sizing for multiple. You don't know how many people are playing. And if an instance goes down, your server goes down, that's multiple game servers that are going down, which could be hundreds of people, which isn't ideal. One thing to note on networking before we continue is that for most games, they're low latency, so you tend to use UDP protocol, and also a static IP address is needed. So in terms of industry challenges, I work with lots of games companies, but when it comes to multiplayer video games, there tends to be a set list of challenges that I see. So the first one is that multiplayer games tend to be global, and if you're really lucky, you're scaling to tens of millions of players. And if you actually want to make money out of it, you want to do that as cheaply as possible, which is surprisingly difficult. The second thing is that player numbers are very, very difficult to estimate, especially on launch. And it's because if you're global, you're region-based, when are people waking up, when are people going to bed, there's a blackout, there's school holidays, all sorts. Your player numbers are very, very variable. The third challenge is that online games are often the subject of DDoS attacks, whether that's a single person, an entire game, all of the servers in a game or a region. It happens quite a lot, and it's quite prevalent in the space. And finally, player expectations. So online multiplayer games have to be online, they have to be accessible, and they are often a social and competitive experience. I know for me, at least, very competitive. And that means that if you can't access them, you may put that game down and never pick it up again, especially if it's a free-to-play game. That becomes a big problem. And then when you're with a group of friends and you can't access that game, instead of the rest of you playing it and leaving one person out, you may all just decide to never play it again and go play the game with your friends that you can actually get to. So now that we've seen these industry challenges and the technology challenges, I'm going to hand over to Flamur to discuss potentially how we can tackle those.
Thank you very much, Ria. So we considered what a game server is and how does that look. And it would not be surprising to actually figure out that a game server looks very much like a monolithic traditional application. And we're basically trying to migrate that to run on a Kubernetes workload. So some of the things that we'd be looking to achieve are things that we look at other workloads as well. So we want to optimize the availability of the service. We want to scale it as much as possible, especially considering like these popular games that go to tens of millions of people. We want to be able to scale, but also be resilient so that we can deploy to different regions, different availability zones, and we want to also increase the productivity of our developers. So what does this look like if we actually dive deep to every one of those categories? So if we're considering the build phase, consider every other application that you have. You actually want to build, but in the game space, the operating system and the size are your two main constraints. And the reason for that is there's going to be games which are Windows games, for example, and they need to run on a Windows server. There are going to be games that run on Linux, but a lot of the games tend to be very big in size. That's like tens of gigabytes. So then you're looking at how do I make my container image as small as possible. The benefits, though, outweigh those risks. So if you're building a container image which runs your game server, then you're basically making a portable image that can run across different architectures. You can build and run on different systems. You can scale. So same as with your other workloads, actually your game server becomes part of your CI/CD pipeline. You build it and part of the same flow. This is now very important when it comes to the deploy phase, which is, for example, for patching. So as we saw with the traditional servers, you actually tend to do manual patching. You go to the servers, you associate it to the console, you change it because there's tens of thousands of people connected. You want to make sure you don't kill the server that's actually serving workloads. In the case of running this on top of Kubernetes, it actually becomes simpler because we can do rolling updates of, say, our idle service. We can release with a CI pipeline and then follow a regular CD process. We can do the same as we do with the rest of our workloads. As the previous speaker already mentioned, there would be loads of other services that we connect to. So we want to actually orchestrate all of that lifecycle. And then we follow things which are normal for everything else, like we do GitOps, and we actually release on the go. Now that we've built and deployed our application, we need to run it. So from a management perspective, it becomes interesting because you want to be able to deploy to whatever your set of fleet. But when your requests come in, you want to scale up. So you want to be automatically scaling. You can use things like Carpenter or Cluster Autoscaler to actually then scale your workload and scale the nodes under it as well. You get benefits from the standard observability tools that come with your clusters. So from like the Prometheuses and Grafana's of the world to things like plugging into a CNI and getting all of the metrics from a network perspective. So you get all of the features that Kubernetes gives out of the box for your workload and game servers as well. One critical thing to consider is that when we're talking about a larger box, as Riha said, when that one dies, that's your failure domain. That is hundreds of servers, all of your players disconnected. When you're actually deploying pods for a game server, then your pod becomes your failure domain. So if that one individual pod dies, then the players connected to that one pod get disconnected, but the rest of your fleet is actually still running. So from that perspective, you're also automatically managing your workload, but also like lowering your failure domain size. And lastly, when you're deploying, you want to be able to, especially with like famous games, you have players which are global. So you want to deploy as close as possible to your gamers so that they have the lowest latency. That means you've got cross-region deployments, and that means that you actually can use your same CI/CD pipeline and flow so they actually propagate your same workloads across different domains, and it all looks the same. It's very easy. It's driven by a configuration, which is very different to how you used to do this manually in the traditional world. Now that we've built, deployed, managed, now we want to connect. We want to make our games available to our different players. And that's the interesting part, because in addition to them coming to your games, you want them to be able to, as I said, go to their closest region, lowest latency. You want them to be able to fail over in case that one server dies, so that they can go back to the nearest possible server next to that and actually still continue to play. And you get all of the benefits that come out of the box from a standard networking setup in Kubernetes. So by using CNI, by using rate limiting, throttling, you actually get to do DDoS protection out of the box without needing to do anything on top. They all come for free for the services they use. And the last point, which is important in this line of business, is we actually want to make this as cheap as possible, because the cost efficiency of such a system, especially at that scale, is very important for a lot of these companies. Also, when you are starting with a new game and you actually don't know if it's going to be a hit or not, you don't want to scale to tens of thousands of servers. You want to start small, you want to make it available, and then if there is actual user interest, then you want to scale up. So scaling only when needed becomes very important. Using things like spot instances or other purchase options becomes very important as well, because you want to run this as cheap as possible. And last but not least, different architectures. So you're able to now, because we're making a portable system, you're able to run it in different architectures. Especially for games, it's important to use things like Graviton or ARM processors, because they're much more processor, CPU friendly in regards to those workloads. So these are all things that you'd benefit out of the box by just running your game server inside of Kubernetes, instead of actually running it on top of a traditional box. That brings us to that last section there, which is the DOMs. So we all are here for the Kubernetes Community Summit, and we want to run everything on Kubernetes, but there are things that should not be on Kubernetes. So do not run, say, persistent worlds on top of Kubernetes. That is a generic statement, but these are, as I said, game servers as is are much more traditional workloads. However, the persistent worlds tend to run for days, weeks, months. So this is a software system that is going to keep on running. And if it doesn't, sure, you might do memory checkpointing, you might externalize your state, but there's still going to be a blip. So you're going to affect your actual user experience. So those are not good workloads to put onto Kubernetes. The next one is if you've got a high frames per second kind of system. So if you've got games that are playing at 60 FPS or more, then you can't really achieve that performance by running the whole stack that is Kubernetes and putting that through network. In these cases, you try to run a server on the edge as close to your players as possible. So that's also another use case. And lastly, if you don't need the complexity or don't have the knowledge. So if you're running a game server for your friends, do not put it on Kubernetes. If you don't have the knowledge, do not put it on Kubernetes. If the system that you're running takes less management effort than the whole cluster underneath it, then that's not a good use case. So with that, we're just going to look at an example architecture. I do have a demo. This is not what I'm going to be running and or showing, but this is just an example, because different companies, different environments tend to do this differently. Especially with our gaming customers, they all have the way they do this. But ultimately, you're looking at, say you've got clients which are geographically dispersed into different regions, countries, continents. They tend to go to a central point, because you do want that. You want to be able to go to one well-known IP address or domain name from a server perspective. That one then, as a CDN, for example, is able to direct your traffic to your closest region so that you're able to run with it. And then when you get to that closest region, whatever it is, say for us would be US1, then you get to a load balancer, which takes you through the different options of the servers that you have, and then you get sent to your actual game server. In this case, we're running different EKS clusters, which are running different node groups. Some of them are Carpenter managed, so that auto scales. Does anybody here not know what Carpenter is? Okay, I'll give a short description while I'm doing the demo. And then you've got things like game state management, which actually helps with externalizing that state and storing that onto a centralized database like DynamoDB, for example, which is then a NoSQL database you can scale horizontally and do cross-region as well. So with that, I'm going to leave this here. So if I have piqued your interest at any bit, we're going to actually play a game. I know this is one of the last sessions of the day, so we wanted to make it a bit more fun. It's a racing game like Mario Kart. It's an open source game, and we're going to actually deploy a containerized version of the game server. We're going to all connect to it and then play the game. So I'm going to leave the QR if you would like to scan or download. As I said, it also works from your laptop, so if you've got your laptops, you can install it there as well. I'm going to play from my laptop. Carpenter, I'm just going to say 2 words about it. Like, you know what cluster autoscaler is? And the cluster autoscaler scales the underlying hardware, whatever that means in a cloud world, that would be EC2 instances, to then match the requirements of your workload. HPA does the scaling of the pods. Cluster autoscaler does the scaling of the actual compute. Carpenter is like cluster autoscaler, except that cluster autoscaler works normally with the autoscaling groups, versus Carpenter does a lot better at bin packing and works directly with EC2 instances. So in that case, then you scale much more proper in regards to efficiency, which is why it's very important for things like this, because then you're able to bring up an instance size with a perfect sizing of like CPU memory, whatever the requirements of the workload are, so that you can actually run it as efficiently as possible compared to the rest of the workloads. So with that, let's see if this works. OK, you do see my screen. So before we go to the game, I'm just going to show you quickly what we have running. So all of you should be familiar with this. Let's try and make this a tiny bit bigger. This is good. OK. That's good. So what I have deployed is a EKS cluster. And inside that cluster, I have deployed Carpenter. And inside that cluster, we're also going to deploy, there is a software called economies, which allows us to actually deploy different game servers as what they call fleets, is a CRD concepted controller that actually manages software. Then it allows us to connect. It basically creates node ports for all of the different game servers, allows us to connect to that game server, manages the lifecycle, manages the patching, releasing, etc. So I'm getting my game servers, just so that you know what I'm typing. It's game servers, and there's none in the SDK namespace. So, I'm sorry, it's like dark here, trying to scoosh to see what it is. So that's my manifest. We don't need to go too deep on it, but basically I'm deploying a fleet of game servers. I'm going to deploy an initial player capacity of, say, 20, get a port. There is the image that I have built, and is a multi-architecture image. So I have deployed, I have built 2 different images using a very regular CI/CD pipeline. It's actually part of the repo. It's open source. I'm going to put the QR code at the end of this. You can see everything I've deployed as part of the demo. You can play around with it and deploy it yourself as well. It basically creates a multi-architecture image for both ARM64 and AMD64. And then by just using the node selectors, actually we can drive, say, for example, some of my game servers are going to run on ARM, others are going to run on AMD. And we're actually also able to, like, say, go between the traffic between the 2, etc. So it automatically works out of the box. There is a autoscaler with this, and you can also tell it to keep a buffer, so it always keeps one more, say, replica in order for people to connect if the first one dies or gets more traffic or whatever. And you can also, I added a configuration which then drives, for example, my server name or my port or users. So I'm just going to deploy this. So I'm going to deploy the AMD version, and I'm also going to deploy the ARM version. And after a tiny second, we should now see 2 game servers here. One, 2 seconds, 8 seconds. They just game gets scheduled. They're running in 2 different nodes, as you can see by the address. And if I look at my actual nodes, you'll see that one of them is a C6G, which is a Graviton instance, and the other one is an R7i, which is an AMD instance. And my workload is actually load balancing between 2 different architectures by just following a standard CI/CD pipeline. I wanted to show you also like my image that I built. We can also go into the pipeline if anyone's interested after the talk. But basically, this is a multi-architecture image index for the 2 different architecture images. And this all gets built out of the box. So with that, I'm going to get our game server. So as you can see, we have one here, which is allocated. I intentionally allocated that so that we can actually start playing without any issues. And that's the game server and the port. So if you all go to, it'll just show you this. SDK. Unfortunately, my other domain decided to not work today, but this is the other one. So if you use the name sdk.gogoli.com in your game server, I'll show you how to do that. Then you're going to be able to connect to it. I'll show this now in the game. So if you've downloaded, installed, this is what the Super Tux Card game looks like. And if you go to the online, you don't have to create an account. You can just say offline for the purposes of this game. And then if you go enter server address, then here is where you put it. You basically type sdk.gogoli.com, and then that's the port. Now, before we start playing, just like want to drive a couple of points here. In a real world, if you were to run game service, you wouldn't want your users to go in, because they don't have access to your console, right? They can't see the port, they can't see the name. They would get access to what's called a matchmaking service. The matchmaking service then actually finds out all of the servers that are in the backend. They actually pair you with, depending on, say, your latency, depending on your skill set, they will pair the players together and then collect them to one single server and then redirect that traffic. Of course, for the purpose of this game, because that's built into the game itself, I didn't want to go and change the code for this, but ultimately, this would all be like automated for you. Or like this would be, some of these servers get registered automatically with the game. You make them public, so then they're available for you to pick when you're running. And if you have put sdk.gogol.com, the port 7206, should I start? Everyone ready? No one's... Yeah. Whoa, that's a lot of people.
Huh.
That's quite a lot of interesting parties. I'm liking this. So I have no intention of trying to decide to win, but whoever Drew is... Yes, whoever Drew is, so the first person that joins becomes the owner of the server. So you can start the game.
We've given you unprecedented power. Do what you do with it.
So you can play, and then you get to pick a character and a car. Okay, I'm gonna be this because why not? And then you can all vote for a track. So you're welcome to pick whichever.
Might want to set the number of laps to 1, but
Do set the number to 3.
depends, you know.
Yeah,
Never have too much Super Tux Kart.
Okay, here we go. You do use your, if you're playing on your laptop, you use your arrow keys to drive, and then you use your space to shoot things. Some are driving faster than others. I don't know why. Someone is cheating. Whoa. Somebody ran off. Oh. Oops. Don't steal my... Okay, thank you. We're going to finish in 3.
Yeah, I feel like Drew's
I'm just checking whether I can fly, but apparently not. So while that's playing, I'm going to let it play because I don't intend to win. Is there any questions? We've got about 5 minutes. We don't want to distract the people who are playing, but...
Yeah.
OK, if no questions, then... Apparently, I'm number 13. That's not a good starting point.
Oh, it's a lot of people, yeah.
And I think you use N for using the Nitro if you're on a laptop.
See, he never told me half of these roles, and I feel like...
It wasn't for you. It's for the audience. Somebody slowed me down. It wasn't me.
So in this game, all of the actions are all of the inputs that you're putting in. And again, if you're getting any jittering or any latency, that's because your client isn't the one deciding what's happening in the game, essentially. And so when you have a better optimized game, it doesn't tend to jitter as much because you have things like netcode or other things that will make the game run a bit smoother. But
I mean, generally speaking, this is actually not bad considering it's a pod running in a EKS cluster. It's deployed on EU West 1, if I remember correctly, which is Dublin. We are running a pod which actually does have certain level of resource requests and limits. It's not much. It's like a CPU and some gigs of memory, or less than a gig. We're 13 people, so it does seem like we're all in the same network, but every one single device gets their own connectivity, and it's managing fairly well, right? And imagine scaling this and running to tens of thousands of users. So from that perspective, as I said, I'll show a QR code with the actual code, but ultimately it's a build pipeline using code pipeline and code build, which is automated. It builds the server on top of a Debian base image and actually runs it on top of an EKS cluster with a couple of applies. So this is giving you ideas on running your own game service. But
in the big scheme of things, running the game service is the easy part. Actually making any money in the games industry is the difficult part.
So, are we anywhere close? I think I'm lap 2.
No, lap 3.
I'm lap 3.
Nearly done.
I'm feeling conscious of the pictures being taken showing us playing. Were you there to black or you missed out?
And we're going to leave these servers up. So if you are so inclined and you feel like you want to go for the crown with some of your friends this evening, I'm sure if you've got.
I might put in a password though, and if there is a password, it's going to be KCD UK, all small, just to not leave it open. But I didn't want to add that for the demo. Thank you very much for your time. I hope you enjoyed the session, and yeah, see you later.